structures are in uniform cross section. I mean, when the specimen subjected to tensile load or compressive, the first equation valid. When the specimen subjected to bending, then second equation will be valid. When the specimen subjected to torsion for finding the stresses, the third equation will be valid, right? I mean, when the specimen in uniform cross section without any discontinuities. Suppose that's what that's what we discussed in the yesterday class. And when we discussed in the previous chapter, theories of failure, when the specimen subjected, we considered the right side of the failure equations, all 5 equations in the right side, we considered the specimen tested under the standard condition, standard testing specimen. During that time, a simple tension test and shear test we considered for the defining those theories. But now still we thought at that time that the right side the stress component, the stress magnitude was more like that in the earlier. But now when the discontinuities are presented, now the localized stresses developed in the nearby the discontinuity. For example, in the vicinity of the hole, I mean, the stress magnitude is more as compared to the elementary strength of formula, using elementary strength of concept, using for example, simple tension test or compression test. That's what yesterday we discussed. Now today we are going to discuss furthermore. I mean, what are the stress concentration factor? How to choose different load condition? How to choose the stress concentration factor? That's what we are going to discuss. And few more information. How to modify our design of the component to avoid the stress concentration. Those things we are going to discuss today. Okay. I mean, what is the stress concentration factor formula? Anyone, please tell me. Stress concentration factor formula. What is the stress concentration formula? Sorry, guys. Please tell me, someone. What is the stress concentration factor? Yeah, a very simple formula. No? Yesterday we discussed it, right? What is the stress concentration factor? All of you there in the meeting?
Yes, sir.
Yeah, please tell me, Pa. What is the stress concentration factor?
Sir, sigma maximum by sigma naught.
Yes, exactly. I mean, the sigma max where we focused, I mean, where the discontinuity presented in the component, at that place we observed the stress magnitude, that is sigma max. I mean, sigma naught is our standard standard equation. We are using the standard elementary strength of material concept for measuring the stress, that is sigma naught. Okay, anyway, thank you, Pa. Thank you. Sorry. Okay. This is the things we discussed. What are the parameters to be considered for reducing the stress concentration factor? We discussed in the yesterday class. I mean, that is variation of properties of material, load applications, I mean, abrupt changes, change in cross section of this material specimen, discontinuities are presented in the specimen, the machining cracks, that also big impact for the stress concentration. We have seen the one video also. Okay, now we come to this this one. Now actually stress concentration various geometries. we discussed yesterday why elementary strength of material concept we can't apply. Then we discuss in general what is the stress concentration factor. Use, for example, we discussed about the simple plate with a hole, right? But today we are going to discuss furthermore depth. We are going to discuss more and more depth today. I mean, the stress concentration factors determined in two methods generally. One is mathematical method based on the theory of elasticity concept. I mean, theory of elastic concept mean experimental methods by using a photoelastic concept. I will show you a beautiful one video. You can clearly understand. And second method, we can use FEA package to understand the stress concentration at the different loading conditions, at the different boundary conditions. But FEA method, it will give you approximation because it will not give you exact result, but it will give approximation, at least 80 to 75 to 90% approximation as compared to practical conditions. Okay, that also depends on applications. But we hope that we can learn something from the FEA package. In this, where it is the stress concentration factor, we can easily modify the boundary condition. We can easily apply the various type of loads to study the material behavior. Okay, now here the stress concentration factors are rectangular plate, a transverse hole loaded in the compression. I mean, we are going to see briefly in that at which condition we have to use stress concentration factor value. For example, at which condition the bar, for example, the bar may be subjected to tensile with hole. The bar may be designed with fillet. The bar may be subjected to bending. The bar may be subjected to torsion. Then during that time, how to choose this stress concentration factor, that we are going to discuss today in the upcoming charts. See here the normal stress. This is a nominal stress in the circular hole presented in the small plate. I mean, stress is equal to P by W minus D into T. This is a nominal stress when the not thin or thick. So in general, the plate having thickness T and this hole is presented in the transverse direction. Okay. Now this is a nominal stress. Now the second case, the stress concentration factor for the flat plate with the shoulder fillet. Now the first case, the equation 5.2. This case, I mean, the plate is uniform width and uniform length. It won't be any shoulder, but only hole is presented. But second case, the plate with the fillet, I mean shoulder fillet, then subjected to compressive and a tensile load. Then this is the nominal stress P sigma naught is equal to P by dt. This is you might have been studied already. Okay. Now we are going to use how to select our stress concentration factor based on applied load condition, based on our plate design. Now one by one, see. I mean, before going to that, we are always saying that we discussed last class also, this class also, few things about, I mean, that photoelasticity concept, right? Now, just you see this video, you can understand why I am unable to select this. Are you able to see this? Are you able to see my video?
Yes, sir.
Yes, sir.
Yes. See here. The guy is holding, they clearly explained here, the guy is holding photoelasticity and in 20 mm acrylic with the polarization. Now see this, he is going to fix it in the plate. This is our acrylic plate. Now without a stress, now the material is not at stressed now. Now the epoxy plate is not stressed now. Now they are going to making machining. During that time, you can see the more stress will be created. You can see it looks like magnitude increment, increasing the magnitude somewhere. Wherever increasing the magnitude, there are more stress concentration. Now see here, the drilling is performing here. He is making drilling with the help of the drilling tool. Top, you can see the top. I mean, see here, in the tip of the drill bit, more stress concentration. Yeah, now see here, you can clearly see this. The tip of the drill bit, you can see this here more stress concentration. I mean, it can be observed with the help of the photoelasticity concept. Okay, the tip of the drill bit more stress concentration, it can be observed with the help of the photoelasticity. Okay, now this is whatever we just now we discussed. This is the plate thickness T subjected to transverse hole here, diameter small d. Okay, now see this. I mean, this graph obtained by the people who might have been done enough number of research and experimental they might have been performed, then they came to final conclusion. Then we are there straight away we are using this for our application. Suppose the plate thickness is, plate diameter is, plate width is W, and the internal hole, transverse hole is a small diameter D. When the D by W ratio is changing from 0 to 0.6. Okay, now my D by W ratio is, for example, I tell my example now the P by D by W ratio may be 0.4. Now we have to choose the stress concentration factor. For example, this is my P by ratio. This I am considering 0.4. My D by W ratio is 0.4. Then what is the stress concentration I have to follow? I mean 2.25. 2.25. Then 2.25 my stress concentration. Sorry. Now 2.25. Now what is my sigma max now? My sigma max. What is my sigma max now? Sigma max is equal to KT into sigma naught. I mean, this is a stress is going to be developed in the nearby the hole. Then based on that, I have to design my component safely. Okay, based on this chart. See, keep in this mind. This is very important chart. Okay, you have to learn this chart. There are 5-6 charts are there. You may expect in the objective questions, objective exam also you may expect this type of questions. So, okay, now this stress concentration factor is 2.25. Now, this is for both tension and compression. When the plate presented in the discontinuities in the form of hole. I mean, when the plate subject to tension and compression, we can use this table for finding. We can use this plot for finding our stress concentration factor. Okay, at a different, width and diameter of the plate, different width and different diameter of the hole in the plate. Okay, this is the plate subjected in tension and compression. We can use this formula. One more video. What is this? Yeah, this is yesterday I showed this. Did I show this video yesterday?
Yes, sir.
Okay.
Yes, sir.
the corners, how the corners are getting more stress magnitude. You can see that video. I will share you in the LMS. Okay. Now I come to this next condition. I mean, we are going to see that, I mean, the flat plate with the fillet and tension compression, then round bar with the fillet with the tension bending and torsion. We are going to see each one separately. Okay, now this is the equation, general equation what I have shown here. We are going to see this tensile force, bending moment, torsion moment. Based on that, how to vary the stress concentration factor, we are going to see that. Now see here, there is a slide, this doesn't matter. Now see this, I mean 5.2 figure, this figure already we discussed. Okay, now come to the figure 5.3 here. This figure, in this figure, a stress concentration for flat plate, shoulder fillet. Here they are given shoulder fillet in tension and compression, while the shoulder fillet with flat plate and subjected into tension and compression. Using this graph, we able to understand, we able to find our stress concentration factor here. Okay, now see here that there are, I mean, there are 3-4 graphs are there in this plot. I mean, each one is representing the capital D by D. Capital D is nothing but our larger diameter, width of the plate, capital D, and this is shoulder region, plate, width of the plate, small d. Then when, for example, now I am taking, this is a fillet radius, or small r is our fillet radius, small r is our fillet radius here. Then R by D ratio in the x-axis, y-axis our stress concentration factor. But here what we have to consider while designing the components, we should know capital D and small d, right? Then we should know this R, small r value. Okay, then if you know, for example, I'm taking 0.2, my small fillet radius and my shoulder region width is small d, the ratio between r and d is a 0.2. Then but capital D, my small capital D and small d ratio going to be 1.5. Then what is the stress concentration factor? I choose my component design. You see here now 0.2 corresponding 1.5 here 1 point. This is 1 point here not given. Yes, okay, 1 point. Okay, you take it 1.2. D by D ratio is 1.2. See here, D by D ratio 1.2. Then the stress concentration factor 1.8. I have to choose. Okay, just here 1.2. This is my stress concentration factor 1.8. I mean, when the flat plate subjected into tension and compression with the fillet, very important. Without a fillet, you should not use this table. We have to use this earlier table. Now I come to the next table 5.4. I mean, see here 5.4. Now the round shop subjected to tension. Now we are discussing the component in round shop subjected into tension. Now is subjected into tension. Here the stress concentration factor, we are going to find it out. Now see here, this is a diameter capital D in the bigger diameter. This is small diameter. I mean, after fillet radius, the small diameter, small diameter is, they put it small d. Then they have given the D by D ratio here. I mean, this D by D ratio, for example, your shaft diameter, bigger dia is capital D, smaller dia D1, small d, the ratio is 1.1. You should follow this curve. You should follow this curve based on your R by D ratio. You have to find out your stress concentration ratio. Stress concentration factor. For R by D ratio, I am considering for 0.2 here. Then what is my stress concentration factor? 1.3. 1.3. Suppose my R by D ratio is my R by D ratio is 0.2, but my element is my component diameter change, geometry is different in that sense. The dimension d and small d going to be value different, the ratio is different. For example, 2, then my stress concentration factor is 1.7. Okay, so very important, this is very important. Based on that, we are going to discuss so many problems in the later. Okay, now, so this is the stress concentration factor for soft, when the round bar subjected into tension, the round bar subjected into design with the fillet. Now I come to the next figure. Now similarly, the shaft, the round bar subjected into bending. Now the round bar subjected into bending, the same concept we have to apply to find out our stress concentration factor. But each graph, this is a standard graph. Each graph, they're having different value for different value because of based on different loading condition, they provided different values. Okay, this case, or only one thing I tell you here. Suppose my R by D ratio, my bending moment is here, acting both sides. Then this is only this plot only suitable for bending the shaft, while bending moment is acting in the circular bar. Okay, in the circular bar, for example, now I am considering, my capital D by small d ratio is, 1.5, this plot here. Okay, so small thing is simple thing I will take because you can easily understand. Now I take this. Okay, I take B, which one easily able to see, that one we can take it. Now 1.1 I take 1.1 here. Okay, 1.1. What is my R by D ratio? 0.1, 0.11, 0.12, 0.14. My R by D ratio is 0.14, corresponding my stress concentration factor corresponding to D by D ratio is 1.1. Then this is my stress concentration factor 1.5. KT is equal to 1.5. Okay, then you can apply this standard formula sigma max by sigma naught. Then you are able to find out what is the sigma max. Based on the sigma max, you have to design your component. Okay, now we discussed about 4 different graphs. Now we move to another one, the last one, with respect to torsion. When the bar subjected to torsion, here this is a torsion, subjected to torsion, then we have to follow the different stress concentration factor. Now see here the R by D ratio, for example, I am taking this 0.1, R by D ratio 0.1, then but my capital D by D ratio is 1.2, then my stress concentration factor is 1.4. When the component is round fillet rod, I am using as a round fillet rod subjected into torsion moment, and simultaneously the dimension ratio D by D ratio must be in 1.2. During that time, I can consider stress concentration factor KT going to be 1.4. Now what we discussed, there are 5 figures we discussed. Now the first, just a brief conclusion, the first figure we discussed about the component in only presented whole, but the component subjected in tension and compression, but in flat plate. That's what we discussed for the stress concentration factor. The second plot we discussed about the component flat plate, subjected into the flat plate with the fillet radius. Okay, then subjected in tension and compression. During that time, how to define our the stress concentration factor. Second graph we discussed. Third graph we discussed about the tension of the round bar, in the round bar with fillet design. Then based on fillet design and the dimension of the shaft, we discussed about the tension, about the stress concentration factor under this circular bar subjected into tension. The fourth plot, what we discussed the that bar, so this round bar subjected into bending moment with the round bar designed with fillet radius. Okay. Then based on the dimensions, we discuss about the stress concentration factor. The last one, the present, this last one, now the same round bar subjected in torsional movement, how to understand this stress, how to find out the stress concentration factor based on this diameter of dimension of the bar as well as fillet radius. We have to define this stress concentration factor from the graph. So these 5 plots are very important. Okay, please practice it. Okay, now I come to the stress concentration factor in due to elliptical hole. But whatever we discussed in the earlier case, I mean the hole also in uniform hole, I mean uniform diameter. But right now we are discussing about elliptical hole. Elliptical hole, how the stress concentration factor varying, you'll see that. A flat plate with elliptical hole and subjected to tensile force, seen in figure. I mean, it can be proved that using the theory of elasticity, that the theoretical stress concentration factor is given by this formula. Kt is equal to 1 plus 2 of A by B. The A is nothing but semi-major axis of the elliptical hole. I mean, B is the semi-minor axis of the elliptical hole. Okay. Now, when the Kt, I mean, when A is equal to B, what is the stress concentration factor in this case? 3. When the elliptical hole, when the A and B are equal, then the stress concentration factor is 3. But when the B is going to be 0, I mean, for example, line, for example, crack, one small crack, vertical crack, that no major axis, no minor axis, right? I mean, then what will happen? I mean, small elliptical crack, oh sorry, major, we can consider major axis, one line, vertical line crack. Okay, then what will happen? Then that the B dimension going to be close to 0, then it will be more stress concentration. We may say that infinite when B is equal to 0. So crack is always more stress concentrations. That's what we discussed. We have gone through one video also. I mean, that video also I presented yesterday. Then the lines are looks like pencil pens we have drawn in the pencil like that earlier before the experiment. But when the crack subjected to load, then it will be the more failure, right? The failure are starting from the cracks because the stress concentration more in the cracks. Hence, micro and macro cracks also important in the design consideration. Okay. Now I come to this. I mean, whatever we discussed, general we discussed. Now, based on material, we are going to discuss this stress concentration factor. Now, see here, some more videos. Okay, see here. I mean, very simple. You can read it yourself. I mean, the stress concentration factor, the stress concentration factor charts are based on either photoelastic analysis. Based on either photoelastic analysis or experimental using circular polariscope or theoretical or finite element analysis. I mean, hence this is called a theoretical stress concentration factor, because in practically even the stress concentration factor, it may be varying while the component going to be in practical condition. That's what we are saying. This is a theoretical stress concentration factor. This is now here the model is made of different material. Then the actual material of the component may be different. Actual material of the component may be subjected into different loading or combination of torsion or combination of bending. I mean, that maybe depends on application, depends on working scenario. Hence, it may vary that also. So that's what we are saying here. That's what. Then not only that, also it very depends on the material properties also. For example, see here the ductility and the brittleness of the material has pronounced effect in the response to stress concentration. Okay. I mean, also the what type of load, whether static load or cyclic load, I mean, subjected in the material. That also important parameter for finding the stress concentration factor. Now see here, I mean, there is a difference between theoretical stress concentration induced by the theoretical stress concentration factor and the actual measurement, actual stress concentration factor. It will come from the practical utility. Okay, I mean, these two things designers should understand. Okay, now what are the things we should understand while based on material, what are the things we should understand? We are going to discuss only. There are two types of material, broadly two types of material. One is brittle and ductile. Means for ductile material under static load. Under static load, ductile materials are not affected by stress concentration to the extent of the photoelastic analysis might indicate. And when the stress in the vicinity of the discontinuity reaches the yield point, there is the plastic deformation resulting in distribution of the stresses, right? I mean, most of the component we are designing, whatever we are designing the component, we are within the elastic limit. Whatever we are stress limit, we are defining the material within the elastic limit. I tell you one example. In the last chapter, we discussed many problems. In the problems, what we discussed, I mean, SUT, ultimate tensile strength, yield point strength. We considered. I mean, did we consider the direct value? No. We used the factor of safety. I mean, ultimate tensile strength divided by factor of safety. For example, 3. I mean, 210 ultimate tensile strength divided by 3. Then we consider as a permissible stress limit 70 megapascal. Like that we use. Hence, even though we are in the, under the elastic limit only. Okay, but when it is reaching, when the more stress concentration, it will be failure, right? More stress concentration, it will be failure means that it will be a plastic deformation, because still our designed component under the elastic region only, because we are already using some factor of safety. Okay, that's what we are saying here. And now the plastic deformation or yielding is local and restricted in very small area. I mean, even distribution, even yielding, the yielding also going to be, even yielding or plastic deformation, it will be very small area in the ductile material. When the material subjected to static load, very important. Static load, the static load means that the load amplitude and direction doesn't change with respect to time. The load amplitude and the direction doesn't change with respect to time. And so during that time, that the plastic deformation yielding local and restricted to very small area. Now, this whatever now we are looking at, we are understanding with based on the static load. I mean, there is no appreciable damage to the part as well. I mean, therefore, it's a common practice. Ignore the theoretical stress concentration factor for the component made of ductile material during static load. As well as static load and within the elastic limit. Okay, within the elastic limit. Now I come to the ductile material in fluctuating loads. See here, during fluctuating loads, the stress at the discontinuous maybe exceeds the endurance limit. What is the example? You take one small wire, you applied less stress. You take small wire, just bend it, straight it, bend it. You are applied load also within the elastic limit, but after few cycles, after thousands of cycles, the material going to reach the endurance limit. Okay, exceeded the endurance limit. We are going to study what is endurance limit in the later, but exceed the endurance limit, then the material going to be failure. What will happen? You take very small thin wire, multiple times, bend it, straight it. Finally, the material getting failure because of when you are bending, tension. When you are straightening, compression. Even your applied load is within the elastic limit, but the material is discontinuities. Discontinuity may exceed the endurance limit, then the material going to be failure because of the fatigue. Okay, that is the fluctuating loads. Now, hence the endurance limit of the component made of ductile material is greatly reduced due to the stress concentration. And however, some materials are more sensitive than this stress than other stress, rising the notches under the fluctuating load. To be considered, the effect of the parameters are called the notch sensitivity factor. I tell you a small example. Sorry. Now take one small bar. The bar is, two materials. One material is aluminum, another material is mild steel. Two materials, but same identical bar. The bar is same identical bar. Both are different material. This is notch. Okay, I mean this is the identical material. I am taking aluminum as well as mild steel. Now, which material more sensitivity in this? More sensitivity in the cracks? I mean aluminum, because more sensitivity, because more ductile, right? So the material also we have to be considered, but based on notch sensitivity factor, we can modify our stress concentration factor. I mean, that's what we are later we are going to study this. Based on notch sensitivity factor, we can modify the theoretical stress concentration factor. How it can be modified, we are going to study in the later upcoming chapter. Okay, now I will show you some video here. I think next page. Okay. Now I come to brittle material. Brittle material. I mean, the effort of stress concentration is more in case of brittle material due to the inability of plastic deformation. I mean, see here, you take, for example, we are using two-wheeler. In the two-wheeler back wheel axle, right? The axle, if you made with ductile material, then the ductile material it will sustain. Even it will be a crack is initiated, the crack propagation also it will take some time. Then until if you know that the crack initiation you are able to stop, so you are able to protect your vehicle, right? But if we are using brittle material as your axle in the back side, without any notification, it will be a sudden failure. That's what, because of, I mean, due to inability of the plastic deformation, that the stress concentration is more severe in the brittle material. Okay, the brittle material do not yield locally, and there is no readjustment of the stresses, because even ductile material try to readjust the direction while apply the load. Even some crack is there, try to resist the load even though crack is there. After some time it will be a broken, it will be a failure. But brittle material is not like that. Sudden failure, it's no readjustment of the stress lines. A sudden failure at the discontinuities. Once discontinuity formed, we cannot expect it will sustain some duration. It will be immediate failure only. That's what we are saying here. Hence, this effort reduce the stress external load and also increase the stress concentration. I mean, in the crack, the part of this is going to be a first failure in the brittle material. Now, how here? Hence, the stress concentration factors are used for the component made of brittle material, and subject in both static as well as fluctuating loads. I mean, both loads, even what we discussed in ductile material, fluctuating loads, we discuss how the material going to be failure. Then fluctuating load is very, very important. During fluctuating loads, we should consider the stress concentration factor. But in brittle material, both cases, either in static load or fluctuating load, we should consider for the stress concentration factor. I mean, you can see the beautiful video here. This is a ductile material. See the ductile material. When the load is applied, the material sustained. Slowly the crack is propagating. Finally, going to be failure. Right? This is a ductile material. Now the stress concentration more, the stress magnitude more at the tip of the discontinuity. Tip of the discontinuity, the stress concentration is more. Okay, but if you see this case of brittle material, just I show you this another video. Yes. Right. Okay, now one more video. What is this? This video I will show you in the later. Okay, after end of this today presentation, I will show you. Now I come to the how to reduce the stress concentration factor. How to reduce the stress concentration. Those things we are going to discuss now. Now see here. How many slides? We are going to have a problem today. We're going to discuss. We'll see. Now reduction of stress concentration. See, it is anyway. It's not possible to completely eliminate this stress concentration factor. It is not possible to completely eliminate this stress concentration. There are few methods we can use to reduce the stress concentration for providing the specific geometry. For example, providing the specific geometry of the component. One example. Okay. Now, how do we understand? In order to know what happens at the change in shape of the component or discontinuity provided in the component and reduce the stress concentration under the flow of analogies. Through fluid flow analogy, we are able to understand that. Now we will see here. See here, there is a similarity between the velocity distribution of fluid flow in a channel and the stress distribution in axially loaded plate. Almost many times we are considering the fluid flow analogy for understanding the properties of the solid behavior. Sometimes we are using fluid flow analogy for understanding the solid behavior when subjected into different load. That's what many times we are using this concept. Similar concept we are using here. See here, this figure is a fluid flow potential. This is a flow potential in fluid mechanics. This one, the flow. The fluid flow flow of fluids in potential of fluid flow. This one. The left side figure. This is the force flow around the material. Force flow around the material. See here. In this now. For example, this left hand side, the first one is force flow around the soft corners. First, you consider this portion. When you are considering this portion, that force, when apply the force distributed in each layer of the component, each layer of the material. When the material is bigger size, then the force distribution, means the stressed lines are the stress. Each line is called stressed lines. Each line going to have the less intensity of the forces. But when the sudden changes happening in this material, sudden changes means a change in cross section, then same amount of force again transmit this to material in each layer. Then each layer comes close to each other. Then it will be stressed more. Then the stressed lines are going to have more intensity. Then this kind of structure going to be failure happen. Similarly here also. This is in the fluid flow analogy. The fluid is flowing inside the bigger diameter. Then when the fluid flow changing from this region, section to secondary section, the stepped region, what will happen? The fluid flow velocity will be increased because to maintain the same quantity of maintain the same flow rate of the fluid. Hence, each fluid line, each streamed fluid line, it will be a more intensity. That's what we are using this analogy for understanding our solid behavior. Fluid flow analogy we are using for understanding our solid behavior. Now I have written clearly the point by point, you can easily understand. In the cross section of the channel is suddenly reduced. Just I read this. The cross section of the channel is suddenly reduced. The velocity increases in order to maintain the same flow, and the streamlines becomes narrower and narrower and crowded together. Then it will be a failure happens. This is with respect to fluid flow analogy. Now I come to our solid mechanics concept. How we are using fluid flow analogy to understanding our solid mechanics. See here, a similar phenomenon is observed in a stressed plate. In order to transmit the same force from the stressed line, come closer and closer in the cross section. When the cross section reduced, then each lines are all the lines are come closer and closer, then what will happen? It will be that each line is going to have a more stressed. I mean, each line in that sense, each layer of the component going to be more stressed in this region as compared to this. Okay. Now, see here, the streamlined shapes are used channels to reduce the turbulence. I mean, in fluid mechanics, the streamlined shapes are used to reduce the turbulence as well as resistance to the flow. Okay, in fluid mechanics. But in our case, streamlining or rounding the corners of the mechanical component, the similar beneficial can be obtained that can be reduced the stress concentration. Now you can see here how to reduce the stress concentration factor. Then these are the ways. There are 4 methods explained in your book. I mean, in your book, the same methods in the Bandari, you can get it more information. I'm going to restrict few key points only. Okay, first method: additional notches and holes in a tension member. See here figure. I mean, when we are using single notch, I mean, see here the stressed lines are, I mean, more closer, then it will be a stress concentration more in this region of interest. But see here the figure B, we are using multiple notches, but all are in, I mean, a properly oriented direction we used here. Then the stressed line is more smooth stressed lines we can obtain. Then as compared to A, here the stress concentration will be less. Okay, I mean, see here figure C. I mean, instead of notches, if you use the small holes, I mean, in the proper order, small hole here, maybe a small hole, next bigger hole, next very bigger hole, such a way that they designed, they might have been tested, then they came to this conclusion. Then if we are using multiple holes, now the stressed lines are much smoother as compared to the previous cases. Okay, now this is the more stress concentration. This is less stress concentration. This is very less stress concentration. Now here it can be reduced to more and more stress concentration when you remove the material. Now you are making I mean, circular cross sections are not circular. I mean, it looks like circular design. Then the stressed lines are more smoother. Hence, this is the accepted design for this component. Okay. Now here the reduced, I mean, the smoothen the stressed line to be reduce the stress concentration, also reduce the material also. I mean, we are using, when you are removing the material, I mean, while using this type of design, we are saving the material of the component also. Okay, now I come to the next type. I mean, this is a fillet radius undercutting and fillet radius undercutting. Here now I am saying this fillet radius undercutting and notch for the member in bending. Now see here, and one more thing I would like to tell you here. You may ask this question here, sir, single notch, how it will reduce the stress concentration? Multiple notch, how it will be the, I mean, single notch, how you are saying more stress concentration? Multiple notches, how it will be reduced the stress concentration? I tell you one small example. Take, if line of nails are there, if I keep the nails in the line, are you able to walk on the nails now? Right? Are you able to walk in the nails now? Nails? Are you able to walk on the nails now? Is it possible? In line, it's single line, in row. Because here more stress concentration. But now, if you make it multiple nails in column manner and column and row wise, very close to each other, you can easily freely walk on the nails. Because your body is absorbed, I mean, the nail, your body's, your force, Based on your weight, the stress is not acting at a particular point, particular soft corner. Your body force is distributed for each nails, then you able to walk freely. Are you understanding that? So this way also you can understand here practical condition, you can think of this, then you can easily understand. Now I come to this second concept, a fillet radius, undercutting and notch for the member in bending. Now see here, this is the rod, I mean circular bar, circular rod, stepped circular rod. In this design, the stress line is like this. Suppose if I am providing this fillet radius, the stress line is smoothened as compared to earlier. Now I'm providing undercut. When you are putting undercut, more better, and now it will be reduced more stress. This region will be reduced more stress concentration. When you are putting undercut here, undercut or notch here, then here you are using this combination of notch as well as fillet radius. Hence, it will be a better design. This will be a better design, and simultaneously we able to avoid this stress concentration in this region. Okay, and more clarity and more information is given in your book. Please go through that. And then and the third type is drilled additional holes for shaft. Drilled additional holes for shaft. Here this is shaft. I mean, we are using shaft. In the shaft we are using keyways. The keyways can be used to connect the pulleys. The keyways can be used to connect the hub and flange, right? We can connect the pulleys, we can connect the flanges, we can connect the hub with the help of the keyways, right? That's what the drilled holes and shaft. Here we are using keyways, and the first figure is stress concentration the shaft with the keyway. I mean, this is not good for design because soft corner is going to have a more stress concentration. Now the second case, this original, I mean the drilled holes. The drilled holes, when you are using drilled holes, it can be absorbed this stress concentration. It can be reduced to significant amount of this stress concentration. The third one is we are using fillet. I mean, in the each corner of this, we are trying to use the fillet and avoid the stress concentration. Now see here, I mean here this is the equation is given by developed by the person name is H.F. Moore, the ratio of torsional strength of shaft having keyway divided by torsional strength of the same sized shaft without a keyway. I mean, actually this, I mean, I'm reading the formula, another formula, C is nothing but C is equal to the ratio of the torsional strength with keyway. The rate divided by the ratio of the torsional strength without the keyway in the same dimension of the shaft. Okay, so that will give you C value. But when we are using this design, here the W and the H is nothing but, I mean, the width and the height of the dimension of the keyway. Here, width and the dimension. This is our width of the keyway. Here already given. Here width of the key, this height of the key. Then this way also he defined the C value. C is equal to W by D. This is our width of the key. D is our diameter of the shaft. D is our diameter of the shaft. Okay, and D is the diameter of the shaft, and H is height of the keyway, and this D is our diameter of the shaft. This way also we are able to define C value. Okay, now here they have given this is not good. Here stress concentration more in this design, but in this design when you provide the side holes, it can be avoided stress concentration. But when we are providing holes as well as corners or fillet radius if you are using, then it will be eliminated the stress concentration. Okay, please guys be there in the class. I'm going to take the attendance. Okay, now the one more thing, the last thing, a reduction of stress concentration in threaded members. Reduction of stress concentration in threaded members. Okay, now see here. Now, I mean, this is what is this left side? This is sunk, right? I mean, this is a threaded portion. This is the plane portion is, what is the plane portion? The plane portion is called shunt. Right, reduction of stress concentration in the threaded members. See here, I mean, if you can observe that the force flow lines, the stress flow line, this stress flow line, take this. The force flow line or stress flow line like this, right? I mean, line is bent. It passes from the sunk portion to threaded portion. This portion is called sunk. This portion is threaded portion. I mean, when the force or stress flow line is passing from sunk to threaded portion, it will be a bent. Then it will be a more stress concentration. Then, I mean, we would like to use in between the threaded portion and the shunt, we have to design like an undercut. We have to use the undercut. Then we may avoid the more stress concentration in this corner region of the shunt. This is one way we can reduce the stress concentration. Another way, our nominal diameter of the bolt, nominal diameter of the thread and the shunt will be same. The stress line or the force line will be straight line. That also it can be reduced this stress concentration. I mean, now whatever we discussed the last 4 methods, what we have done here, I mean, here we are modifying the design. We are introducing some mandatorily, we are introducing some of the notches, some of the holes and some of the fillet. We are using to reduce our stress concentration. So this is modifying our design and reducing simultaneously. We would like to reduce the stress concentration. I mean, this is a 4 method. Please go through our book. You are going to get more information. Now, can we discuss the problem? What is time now? Okay, only one problem we discussed, and next class we will discuss another problems. Okay, shall we discuss the problem now? Hello.
No.
Tell me, Kalyan.
No, sir. No.
Okay. Okay. Anyway, we discuss next class. We discuss the problem and the remaining theory and the corresponding problem we'll discuss in the next class. I come to home screen. Please be there in the meeting. Yeah. First, I clarify your doubts. First, I see the chat box. Is there any? Okay. Yeah. Please tell me if you have any doubts. Please ask me that. Yeah, please go ahead if you have any doubt. So what we discussed today, we discussed how to find our stress concentration factor based on load applied in the material. I mean, as well as geometry of the material, based on the geometry, based on the load, how we have to find out this stress concentration factor. First 5 figures we discussed that. Second thing, in brittle material and ductile material, how the stress concentration factor playing. I mean, brittle material in static load, it's may not require. It's not that much serious. But when ductile material in static load condition, it's not that much serious to consider stress concentration factor. And I have told you that some reason. But when the fluctuating loading condition, even brittle and ductile, very important. Even brittle material, even static load and cyclic loading, fluctuating loading, we have to consider the stress concentration factor while designing the component. Okay. That's what we discussed. And later, the last few minutes, we discussed about how to modify our design to avoid the stress concentration factor for mandatorily introducing some discontinuities like notches, like holes, like a fillet, like undercut, right? So this kind of discontinuities we are introducing in the component to reduce our stress concentration factors, to reduce our stress concentration. That's what we discussed today. Then next class we are going to discuss the problem, and we are going to start next thing, fatigue as endurance limit and fatigue. Those things we are going to start in the next class. Okay. Yeah, please tell me if you have any doubt, please. Roll number 1, 2.
Sir, roll number 1.
Okay, 2. Yeah, please.
Roll number 2, sir.
In between, think if you have any doubt. I'm ready to clarify later also. 2 present 3. 3 option 4. 4 option 5.